Okay, visualization of data has been used throughout human history to streamline and communicate complex information, as you can see from these antique illustrations. In the 21st century, thanks to so many new digital tools and platforms of communications, visuals that transmit data and scientific discovery to the public are now prolific. So which graphic tells the story better? The narrative of the image on the right is easier to interpret as opposed to the one on the left. So what makes it better? Here we will address these questions and more. So I'm here with Alissa Park. Alissa, would you like to introduce yourself and tell us about yourself?
Hi, my name is Alissa Park. I'm a faculty member in Earth and Environmental Engineering and Chemical Engineering at Columbia. And I'm also the director of the Lenfest Center for Sustainable Energy. And as you can imagine, we have developed engineering solutions for a number of sustainable energy and environmental problems. Particularly, my group is very interested in addressing climate change by developing technologies for carbon capture, utilization, and storage. Throughout this technology development, we had to talk to a wide range of audience, including the students to other researchers, which I'm more used to, but at the same time, we also had to talk to industry partners as well as potential investors to our technology we are trying to commercialize. So we start talking to Nikki about how to effectively communicate what we are developing in our lab to show that what could be the not only impacts, but what we are visualizing to have what kind of system we want to have. And that has been really fruitful collaboration. And this presentation is to show that how we evolved over the time, kind of trying to understand how to talk to each other to come up with the visualization. And this is not as straightforward as you think. So Nikki, here you are.
Yeah, exactly. So I'm Nikki. I'm the art director in the Office of Communications and Public Affairs. One of my tasks at Columbia involves working with researchers like Alissa, who have a limited time and means to dedicate to creating art. Yet their research requires a certain amount of visual dissemination that is accessible to more than the scientific community. So over the years, Alissa and I have successfully worked together and created clear visuals of some of the innovative research in sustainability that's done at the Park Lab. Alissa, can you tell us about the Park Lab and some of the work that you do there?
So this particular work shown on this slide is the how to extract the metals, like for example, copper and gold from electronic waste. So when you think about electronic waste, I can always show the picture of my iPhone. That's one way to do it, but it doesn't really illustrate scientifically how our reactions and approaches alter the physical and chemical properties of these materials, which is highly heterogeneous, and how we are enhancing the extraction of these materials, which we call it urban mining. So concept is interesting, but we wanted to somehow show that in progress, how our supercritical CO2 based green solvent can be used to extract the copper and gold from these systems. So we went through a number of iterations, and as you can see on the left, even illustrating what, for example, PC board, printed circuit board, it wasn't as easy because the color means something as well as the content, how much thickness of each layer and how quantity of each material exists in PC board. And from there, we had to decide how we're going to illustrate first and second stage reactions. And at the end, you see that there's a different colors as well as a different form factor of the products coming out. So some are solid, some are liquid. And I think a lot of these visualization really help us when there's a really complex reactive system and there's a multiple impacts, both physical and chemical changes. And that illustration really helps more than just words or graphs. And we can definitely have graphs of what was the extent of extraction or extraction yield as a function of different solvents or time and so on. But this was one of the way for us to show that what are the challenges and what are the opportunities and how we are addressing those changes.
As Alissa was saying, pictures can be more efficient than words, especially when communicating complex ideas. Images are universal and can transcend barriers. They allow us to zoom in and out and to see the whole story and the details all at once. Moreover, detecting patterns is an important part of how humans learn to make decisions. Patterns within images allow our brains to know what is important and what is not. In this example, the combined carbon capture and conversion is the focal point. And of course, it's central. Do you want to say something about this image, Alissa? We worked on it recently.
I know. So I think this is the 13th version of the graph we came up with. So if you look at here, all the colors and thickness of the arrows and everything matters. So basically this particular technology is coming up with capturing CO2 directly and convert it to chemicals and fuels, which is shown bottom right. So we wanted to show molecules to show that we are going from one carbon with only oxygen attached to we are adding hydrogen to it. So now you have materials with carbon and hydrogen. So there's less red dots on the bottom right, or there is red dots, but still you see white dots as well. So we show that there's a chemical change, but a lot of these systems, as Kelly mentioned, you sometimes have to use graphics because you cannot see it with your naked eye. So for example, that inset you see right there in the middle is our nanoscale materials, how it's facilitating capture and conversion of CO2. And the arrows going from left to right, which is kind of red to blue, we are trying to illustrate that there's a high concentration CO2 coming in, but then you will have a CO2 lean air leaving the system. But as you can see, we also wanted to illustrate that this approach might be able to show the circular economy of carbon. That's why there's overall circle. But at the same time, we wanted to show that top red arrows are much lighter color because the concentration in that stream is a lot lower in CO2 concentration than what you're starting with at the bottom. And we also put the renewable energy at the top, but it's not within that green box because that's not the system boundary we are looking at. So each of the box, each of the color, each intensity of the colors means something when you try to illustrate your technology or your concept.
So I wanted to go over the first assignment I ever got from Alissa, which was quite a long time ago now. It was to create a graphic that depicted the process of recycling slag, which is the byproduct of steel. This is the final image. Alissa, can you talk a little bit about this graph?
Yeah, so this technology we developed was, if you look at the left and right, this is how we decide. So there's like a current versus future technology. So on the left-hand side, or right in the middle, is how iron and steel plant are making three major products or examples of products. That doesn't change. So we still have the steel manufacturing technology, but the question is how to make them more sustainable. And that's one of the technology we developed in our lab. So if you look at the left, you want to illustrate what is the current practice of making steel. So what we wanted to highlight was not how steel is being made, but what are the environmental impact of those steel making. So you see that we picked the three major waste streams in a sense. So first waste stream is flue gas, contains high concentration of CO2, which is greenhouse gases. Second is the waste heat. And third one is solid waste. And what we realized in our technology development was we can combine flue gas and solid waste and both together, and then maybe we can make value-added materials while managing carbon emission. So you can see that on the left-hand side and right-hand side, they're mirrored in these three arrows. And there's a reason waste heat is smaller arrow, because it's less of a quantity or the impact in a sense. But then the color on the left-hand side and right-hand side is different, because left-hand side, these three major streams from steel plants are considered to be waste stream. They either landfill or they emit into the environment. So that's why we put into gray on the left-hand side. That's our current practice. But now what our visualization or vision is that instead of looking at them as a waste stream, can we look at them as almost unconventional resources? So on the right-hand side, now as you can see, we changed the color. So now CO2 is not a gray color, it's blue, and then slag is green color instead of gray again. So then by starting from same stream, but then now we are viewing differently by putting the colors to them, it means something. And then from there, we had three sets of the reactors. The colors inside the reactor is also very carefully selected, and we try to illustrate how we do the reactions. And one of the important thing is on the most top right, most right-hand side of the reactor, there are three major reaction products. The size of the arrows are designed so that to illustrate what is our major product. And then color for minor element is selected to be really vibrant, because we really wanted to show that that's one of the area we are investigating to improve the overall sustainability of the process.
Alissa, how did you use this graph? How did you end up using it?
So generally when I give academic talk or seminars at the conferences and invited lectures at the different universities, I don't usually use the graphic like this, or only until the end. Maybe I will show as a, this is how we are commercializing, or this is our vision. So this is more vision statement, not the data figure.
Mm-hmm.
So I don't usually go into this, but this was the really nice way of showing industrial partners or somebody who really want to just get the concept very quickly.
Mm-hmm.
This is how I showed, because
Right.
with this figure itself, I can show that how reaction can be processed and how many reactors are involved and what kind of products you can make using what feedstock, and what quantity of materials may go through in these of the entire processes. So usually when I work with somebody who's not really in the field, I usually start with this picture.
Yeah, great. So making that slag chart went through many iterations before it was perfected. This was a new technology that I wasn't familiar with. So in order to explain the process to me, Alissa drew this sketch. So this is the first sketch that you gave me when I met you.
Mm-hmm.
Yeah. I've kept the sketch for many years because I've always loved it. I just thought, wow, this is a beautiful sketch. So in the most literal sense, a sketch is simply a set of marks laid out in a meaningful pattern like a map. So let's dissect what Alissa's sketch communicated to me. The entry point of my gaze was at the very top, since that object was centrally located and apart. Then it moved to the dotted lines around the three rectangular shapes on the right, and then to the bracket on the left, and the objects within that bracket. Finally, my gaze went down to two distinct sections at the bottom. Basically, I chunked the image into bite-sized sections in order to make the whole sketch easier for me to digest. So overall, the three rectangular shapes within the dashed lines are the largest and most detailed part of the whole sketch. Clearly, they were the focal point. Two rectangles contained textures while the third was blank. So the textures indicated content within a liquid depicted by the wavy line at the top, right? That always depicts liquid. The textured contents of the first rectangle had a darker value and they were bolder. This indicated weight or abundance and became lighter in the second rectangle. Their arrows moving from the left to the right conveyed direction, path, and process. This mechanism was going from dark to light or from more solid to less. Finally, there were arrows on top and on the bottom that indicated input or additions to the liquid and content. In order to clean up and refine Alissa's sketch, I needed to consider these things: audience, context, narrative, actors, well, audience, context, path, actors, and clarity. So when creating visuals, it's important to know who the target audience is. Here are some questions to ask yourself. How familiar is your audience with the subject matter? Who is your audience? What is your desired outcome? So it's not an easy task for scientists to simplify or reduce complex research. Finding the sweet spot can be difficult because there is a possibility of either being too simplistic for experts or too complex for the general public. Alyssa, would you like to talk a little bit about, is it simple for you to condense your research into something very simplistic that someone like I could understand?
I'm not sure. I mean, this is always a learning process, I think. What I realized, especially at Columbia, I end up interfacing or communicating with a wider range of audience, in my opinion, because even some of the scientific talks I give, this one is unique because I don't usually do visualization talks, as well as a lot of our panel discussions and presentations on campus are open to public. And I think that's a good learning curve for us, or learning experiences for us, because at the end of the day, science should be communicated among experts. But in order to really have a high impact, we need to learn to communicate our science with not only public, but also policymakers. For example, a lot of environmental technology development, for example, climate change related carbon capture and storage in my group, we do want to talk to policymakers eventually, or at least communicate with them so that they understand where the technology stands, so that whether they can make a policy so that we can move the technology forward. A lot of technology development is kind of pulled by three dimensions. Technology should be there, advancing science and engineering, but there gotta be a market as well as policy. So I think Columbia is very unique in that even engineers have in mind, although we do really fundamental engineering and science research, we have a good communication with the other two pillars. So for example, in this reactor system, you're showing left as just a big black box versus right-hand side with a lot of details. Definitely we teach our students and do research on every little bits and pieces of the right-hand side. There's how to design the impeller, what dimension of this reactor has to be, how to introduce different reactors and remove different products. There's a lot of complexity going into, and in fact, even a little piece of that can be entire PhD thesis. But at the end of the day, when you try to address the question, what they really want to know, what are the grand challenges and how we are approaching the problem, and what are the critical piece we really need to focus on. And I think that without losing the details of how we advance science, communicating that is very important and not straightforward.
Yes. So context is how content is packaged. For example, think of a book. It has a front cover and a back cover, and in between is the subject matter. Well, the same is true for a picture. It has an entry point and an exit point, and in between is the important content. Within the content is a narrative or a distinct path from entry to exit. Clear paths are crucial for directing the flow of information. So here are a few examples of common paths. There's a linear, serpentine, convergent, circular, and radiating. Here is an example of a linear path. So as you can see, It is one straight line. And here's an example of a serpentine path. And it zigzags. Here is another example from Alyssa's lab, a convergent path. The arrows converging there. A circular path. Here's a radiating path that is, you know, of course you can use, you can have two paths within one. So this is a radiating and a circular path. So next is establishing the actors. Who is the story about? Who are the players that will travel along the path we have chosen? Just like real movie actors, who is the star, the co-star, the extras? Who is the villain? And what is the relationship between these actors? So the batch reactor is the star in this case, and the slag stockpile is the villain. Is there anything you wanted to say about that? Or no.
So should we call them villain? I'm not sure. Slags.
Yeah.
I guess in a sense, the way we view things is that I was even telling my students in the class the other day that is coal a bad guy?
Mm.
Well, depending on how you view it, although we put the gray color because I want to say that's an old story a lot of times. Coal made us to, or even petroleum made us to build our modern society. So we should be thankful that we were able to find these high energy density materials. The problem was not about this material. These are just materials.
Right.
The problem was how we use those materials. And I think that's why arrows and other boxes are very important. And putting them as a villain is fine, but in a sense that I'll say the way we were using those materials were a villain more than just the material itself. So I think having those comments or those kind of ideas expressed well within the picture is very important.
Yeah. No, but that's a very good point. It was the way we are using them. Finally, clarity is achieved by not adding extra clutter to the diagram. Strong graphics are clean. This doesn't mean that the image should be stark, but rather that each element should have a distinct purpose and not be superfluous. Shapes, colors, and patterns and fonts should be used to drive the message along the path and not just to be pleasing to the eye. So collaboration between scientists and artists is tricky and requires clear communication. Scientists work under tight deadlines and their budgets are capped. They often don't have the means, opportunity of time to engage with an artist. The main thing that drives scientists is the love of discovery and sharing those discoveries with the people who can understand the intricacies. Do you want to talk about some of the pitfalls of working to have graphics made with artists and non-scientists?
As I mentioned, we don't speak the same language. So
Yeah.
I think that language barrier is hard, but it's not only between scientists and visual artists. I think even when you try to do interdisciplinary research between scientists and policymakers or business school researchers or even teachers, college and education, there's a lot of difference in we don't speak the same language.
Yeah.
So in order to really create something together creatively, you need to talk to each other enough length to understand each other's language, what we are emphasizing, how we are emphasizing, and how also that the visualization Nikki prepared will be read by mostly engineers, for example. Then Nikki needs to understand how engineers would understand the visual. So I think depending on that kind of audience is very important. So she can learn from us how I would react to some of her visuals. And I think more learning we do, the process gets easier, I'm sure. At Columbia, it was really nice because we had a Nikki's group to help us. I think it's getting more expensive. So that's a challenge for us. Time, definitely, it does take more than you think because we have to go through a number of iterations. As I mentioned, one of the latest figure we used for paper just submitted took us 13 iterations. So I think start early and have that as, and I think in my group, we also use this visualization exercise to kind of help us to solidify our vision, long-term vision or big vision of our research itself and what is the potential impact. I think as we go through iterations, we even changed our mind on what component we want to add or what component we want to remove. Because as Nikki mentioned, what's in the picture versus what is omitted, both of them are very important in a sense. So that decision was made kind of working with Nikki, and it's a good learning experience for scientific researchers as well as a visual artist, in my opinion.
For most scientists, art is an afterthought. The main goal of the scientist is to discover the knowledge. The dissemination is the second priority. Whereas the main goal of the artist is that of disseminating concepts, ideas, and narratives visually. It's important to bring art into the process early on, as Alissa just said. Many of the exciting discoveries are smaller steps along the way that are hard to explain. Visualization of data, mapping out research can lead to new hypotheses and insights for scientists themselves. Not only that, but artwork can bring in additional funding. In other words, if the artwork enabled success at getting funds, that wouldn't be obtained otherwise. The artwork would become the driver. Artwork needs to move from simply disseminating knowledge that is already codified to becoming part of the scientific process of model building. Finally, as with most things, the more attention and time given to its development, the better the results. So include art at the start. Here are our Columbia, in-house Columbia resources. That's my email, and everybody's welcome to contact me. And there's also our team at Columbia Creative who can also lend a hand. As an external resource, there's an external resource for creating science visuals. There's an online course that's endorsed by the Medical Illustrators Association, and they are offering a special discount rate to Columbia community. So they're offering this course at $79, it was $199. And you can just log into their website there. Okay, well, thank you. Alissa, thank you very much. And I have to say that of all the professors I've worked with, you are really one who's very keen on art and graphics, and you really promote that. And I really appreciate that about you.
Thank you. It's always a pleasure to work with you.
Thank you, Alissa.
Thank you both. That was fascinating. I mean, we work through that kind of thing every day, of course, at our publication, but it's really interesting to see how the process is there.